Hi guys, welcome to another lecture in the series General Inorganic Chemistry. And today we'll be continuing our conversation about chemical formulae and equations as well as stoichiometry. So in continuing these types of calculation, we're going to proceed with interconverting masses and numbers of particles. So let's start off with a question. It says, let's calculate the number of copper atoms in an old copper penny. Such a penny has a mass of about 3 grams. And for this illustration, we will assume it is 100% copper. So here we have our equations, right? So if you recall from our previous calculations, we have our given unit, which is in grams, right? And we have our desired unit in the first set of conversion factor here. We're converting grams to moles. And then for the second conversion factor, we're converting moles to atoms, right? So essentially, we're going from grams to moles to atoms, right? And so that is why we have two different conversion factors. So essentially, the unit that we're trying to get rid of is normally in the denominator, and the desired unit is usually in the numerator, right? So this is the first conversion. And then for the second conversion to atoms, the same is true. So the unit that we're trying to get rid of is in the denominator, and the desired unit, which is atoms, is in the numerator, right? So essentially, we just carry out this calculation from grams to moles to atoms, and then once we do that, and we should get 3 times 10 to the 22 copper atoms, right? So go ahead, plug the values in your calculator and see if you get the same answer. So I like to do the same calculation using statements, right? Because that way we show that we understand fully what is happening. We're not just plugging in values into an equation, right? So let's do the same calculation using statements. So we have to have in a similar fashion our conversion factor. So remember here, we have our 2 conversion factors. Yes, we're going to use them as well. So our first statement is that 1 mole of copper is equal to 63.5 grams, and that is our conversion factor. So remember, guys, your conversion factor has both units, right? It has your given unit and your desired unit. So remember, for the first calculation, we're going from grams to moles, and so our conversion factor must have a true statement which has both mole and gram, right? And so here we cross multiply, right? And so once we cross multiply, as we see here, and then we make x the subject of the formula, right, by dividing both sides by 63.5, and carrying out this calculation, we get moles, right? So here we have the value of the moles, which is 4.7 times 10 to the minus 2 moles. So what we're seeing here is that 1 mole of copper is equal to this amount of grams. So if we have 3 grams of copper, then we clearly would have less than 1, significantly less than 1 moles. And that's what we're seeing here in the calculation. All right, so for the second set of calculations, we're going from, what are we going from here? We're going from moles that we just calculated to atoms, right? I know this slide doesn't look the best, but it has what we need, right? And so here, X is our unknown because we're trying to get from moles to atoms. So we have a different conversion factor here. Our conversion factor here has moles and atoms. And from our chemistry, we know that 1 mole of copper is equal to 6.02 times 10 to the 23, which is Avogadro's number, copper atoms. So the 1 mole of copper is equal to the 63.5 that we saw earlier, grams, but it's also equal to Avogadro's number of atoms, right? So note our units. This is atoms. And so in a similar fashion, we do our cross multiplication and we make X the subject of the formula as we see here, do our multiplications and division, and we end up with 3 times 10 to the 22 copper atoms. So I hope that you actually pull out your calculator and do it this way as well. So let's check to see if we have the same answer that we got before. Yes, indeed, we have the same answer that we got before, right? So I'm encouraging you guys to use statements because that will help you to understand what you're calculating and not just plugging in values and not know what you're doing. So just to repeat here, we're going from grams to moles and then to atoms. All right, so let's see if we can answer this question. It says, what number would you use to convert moles to grams? Right? Moles, notice you're not given any amount of moles or any amount of any grams, like 3 grams, for example. You're not given, previously we calculated 4.7 times 10 to the minus 2 moles. You're not given any numbers for those units. So you what the question is asking is, how would you convert moles to grams, essentially, like just generally speaking. That's A. And then for part B, it says, how would you convert number of molecules to moles, right? So essentially for A, we're going from moles to grams, and part B, we're going from molecules to moles. All right, so if this is what you had, then you are indeed on the right track. So to convert grams to moles or moles to grams, we use the molar mass, right? So we would have used the molar mass of methane. And to convert moles to formula units, so when we talk about atoms, when we talk about molecules, we use Avogadro's number, right? So if we're going from moles to atoms or molecules, for example, we use Avogadro's number. So here in this previous question, we were going from moles to atoms. Notice we went from grams to moles, so we use the molar mass, and we went from moles to atoms and we use the Avogadro's number as seen here. All right, so at this point now we want to talk about calculating numbers of molecules and atoms from mass, right? So as usual, we have a question to help us to answer or to learn how to do this. So for part A, it says, how many glucose molecules are in 5.23 grams of C6H12O6? So further on, you will see that I use GLU to signify or to represent glucose, and glucose is the same as C6H12O6, right? So it's the same thing. So how many glucose molecules are in 5.23 grams? So when you see a question like this, you want to be aware of what you're going from and where you're going, right? So in this case, we're given grams, right? And we're asked to calculate molecules. So in a similar fashion as we saw before, we're going from grams to moles and then to molecules in this case, because previously we looked at atoms, right? Going to atoms, but here we're going to molecules. Okay, and so we have our two conversion factors here because we're going from grams to moles and then from moles to molecules. All right, so again, our given unit is grams and it's in the denominator here. Our given unit is in the denominator of our, this is our conversion factor. And for a second conversion factor, we're going from moles to molecules. And so our given or calculated unit would have been moles from this step, and we're trying to get rid of it. So it's in the denominator, and the unit that we desire is in the numerator, right? So we'd go ahead and plug in these values. So this is our molar mass. Remember, let's go back to this. We need molar mass to interconvert between moles and grams. We need Avogadro's number to interconvert between moles and either atoms or molecules, right? And so we just go ahead and do this calculation, do our multiplications, do our divisions, and then we should get 1.75 times 10 to the 22 molecules of glucose, right? So go ahead, plug in these values and tell me if you get the answer. For part B, it says how many oxygen atoms are in this sample, right? So here, we're going from molecules to atoms, oxygen atoms in particular, right? And so we have a new conversion factor which says one molecule of glucose has six oxygen atoms, right? And based on our molecular formula here, we're seeing that that is actually true. We have 6 oxygen atoms here. And so we have this very simple conversion factor. And or the unit that we're trying to get rid of, or given unit is in the denominator. The desired unit, which is atoms, is in the numerator, right? And so all we have to do is essentially multiply this number, or the number of molecules, the number that we got from the previous question, by 6 in order to get the number of oxygen atoms, right? So as usual, we like to use statements because that is the way we truly know if we understand what is going on here. So in our first calculation, we have our conversion factor, which is our molar mass, right? And as I said before, I'm using a shorthand here, glucose GLU, right? All right, so just to repeat, right? We have our conversion factor, which is our molar mass. Remember, we need molar mass to interconvert between moles and grams, right? And so we cross multiply and make X the subject of the formula, right? And once we do that, we get 1.7 times 10 to the 22 molecules of glucose, right? And that's the same number that we got here, right? So notice here, we don't have the actual amount or the same amount of significant figures. So the correct number of significant figures would have been 1.75 or 3 significant figures, sorry, based on the numbers that we have here, right? So when you are writing your answer, ensure that you stick to the correct number of significant figures, right? But this slide is basically just to explain using statements the same calculation that we did before, right? And so for part B, in which we're asked to convert molecules to atoms, we have to write our conversion factor, which is 6 oxygen atoms is equal to 1 molecule of glucose, right? This is the molecular formula for glucose. And so here we have indeed calculated the number of molecules in the sample, which is 1.75 times 10 to the 22 molecules of glucose. And essentially all we have to do here, cross multiply or multiply by 6, make x the subject of the formula, and then that works out to be 1.02 times 10 to the 23 oxygen atoms, right? So here, these, just to have a little key here, this is oxygen, and as we said before, GLU, glucose, and C6, that's equal to C6H12O6, right? So essentially, guys, the point we're making here is that we use molar mass to interconvert between moles and grams, and we use Avogadro's number to interconvert between moles and either atoms or molecules, right? So in this case, we're calculating molecules, right? But within the molecule itself, here we're going, this part is a little bit new. So far we haven't really interconverted between molecules and atoms, right? So we just need to know here that 1 molecule of glucose has 6 oxygen atoms. That's our conversion factor. And once we multiply, we get our number of oxygen atoms. All right, so the next thing that we're going to talk about is our empirical formula, right? And how we use it or how we get it from analyses. So chemical formulas that indicate the actual number of atoms in a molecule are called molecular formulas, right? So for example, our C6H12O6 that we saw for glucose, that is our molecular formula. Chemical formulas that give only the relative, and perhaps I should have underlined that word, it gives the relative number of atoms of each type of molecule, they are called empirical formulas, right? So what we just saw with glucose, C6H12O6, here, that is our molecular formula. And the chemical formulas that give the relative number of atoms, so we're going to see some examples of that coming up, are called empirical formulas, right? So the subscript in an empirical formula are always the smallest possible whole number ratios. The molecular formula for hydrogen peroxide is H2O2. And for example, whereas its empirical formula is HO. The molecular formula for ethylene is C2H4. Its empirical formula is CH2. For some substances, the molecular formula is equal to the empirical formula, such as water, right? So we cannot go lower than H2O. So I have the same information in this table here. We have H2O2 and the empirical formula HO, right? So what I want to highlight over here, let's start with the hydrogen peroxide. We have 2 hydrogen and 2 oxygen. And remember, when we're doing ratios, we want to divide by the lower or lowest of the 2 numbers. In this case, it's lower. And the 2 numbers here are also the same, so we don't really have to use that rule. And so we divide through with the same number and we get a 1-to-1 ratio between hydrogen and oxygen. And that is why the empirical formula for hydrogen peroxide is HO. Now for ethylene, we have 2 carbons and 4 hydrogens, and in this case the lower number is 2, and so we divide through by 2, and so we get a ratio of 1 carbon to 2 hydrogen, and so our empirical formula here is CH2. All right, so now we're going to talk about empirical formula and the mole. So the empirical formula for water shows that water contains 2 hydrogen atoms for each oxygen atom. And so this ratio also applies to on the molar level. So 1 mole water contains 2 moles of hydrogen atoms and 1 mole of oxygen atoms. Conversely, the ratio of the numbers of moles of all elements in a compound gives the subscripts in the compound's empirical formula. Thus, the mole concept provides a way of calculating empirical formulas. Let's try to make that a little bit clearer. So here we have mercury and chlorine, for example. They combine to form a compound that is measured to be 74% mercury and 26% chlorine by mass, right? And so if, and underline the if, we had 100 grams, a 100-gram sample of the compound, it would indeed contain 74 grams of mercury and 26 grams of chlorine. Because if we have 74%, that means 74 divided by 100 times 100 equals the same thing, right? So if we had a different sample, if it wasn't a 100-gram sample, then we would have to do this calculation in order to calculate the number of grams, but we're keeping it simple. And so using the atomic weights to get molar masses, we can calculate the number of moles of each element in the sample, right? So again, what did we say? What number do we use to convert grams to moles? Well, if you had molar mass, then you are indeed correct. Or if you said molar mass, that's correct. So we need to look in our periodic table to find out the atomic weight for mercury as well as for chlorine, right? So that's where we would find these numbers, right? And all numbers, related to the molar mass, right? And so here, our given unit is 74 grams. And so that is in our denominator of our conversion factor. And we divide and we get the number of moles here. For the second part of the calculation for the chlorine, we're converting grams to moles again. And so we divide through and we get to the number of moles of chlorine. Right? Okay. And so, as usual, we like to look at the statements, right? And so we have 1 mole of mercury is equal to 200.6 grams of mercury. And so we're trying to find the moles, we cross multiply, make X the subject of the formula, and we get the number of moles. And the same for chlorine. 1 mole chlorine is equal to 35.5 grams. And so we're trying to find how much is in 26 grams. Cross multiply and we get our answer, right? So notice that our answer is in 3 significant figures, as is, we have the numbers here. All right. So once we get the moles, we then divide the larger number of moles by the smaller number to obtain the ratio, the mole ratio, right? So here we divide the moles of the lower number, right? So where the two numbers that we're looking at is 0.369 moles of mercury, right? And then the second number is 0.732. So the lower number is the 0.369. And if we divide through by the smaller number, we get a ratio of 1 to 2. So just go ahead and plug in these values and work along with me and let me know if you get the same answer, 1 to 2. And so if we got the same answer, or empirical formula here of the compound in the question is HgCl2, because of the ratio that we calculated here. And so the general procedure for determining empirical formula is this, right? So we're given the mass percentage of the elements, right? And we assume that we have a 100-gram sample. And so we basically just change a percent to grams because of this assumption. And that is step 1. Step 2 says we convert the grams to moles, as we saw, and then to do that we need the molar mass, and that is step 2. Once we calculate it, or once we have the moles, that leads us to step 3, which means we calculate the mole ratio, and so we get our empirical formula. So let's see if you were following. Our question here says ascorbic acid, which is vitamin C, it contains 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen by mass. What is the empirical formula of ascorbic acid? All right, so I would love if you take a second to try to attempt the answer before you look at it. All right, that's how we learn. All right, so here, just a reminder of the general procedure. So step 1 says assume that we have a 100-gram sample. In that way, we convert our percentages to grams, right? So we're given 40.92%, 4.58%, and 54.50%. So if we assume that we have a 100-gram sample, all we have to do is to just change our percent to grams. That's the first step. Our second step is to use a molar mass to convert grams to moles, right? And so here, this is what we have here. We have our molar mass of the different elements, and we converted our grams to moles, as we have seen previously. So what's the third step? The third step is to calculate the mole ratio, and therefore we get the empirical formula. All right, so since the smallest value is 3.406, we divide through by our smallest number, right? And so we get a ratio of 1 to 1.33 to 1, right? And so notice our significant figures, right? So here we have 4 significant figure. The answer is 4 significant figure. Here we have the lowest significant figure is 3. We have 3 significant figures here. So the ratio for hydrogen is too far from 1 to attribute to the difference in experimental error. So what happened is that, recall when we had, what was it? Here, right? Here we had 1 to 1.98, and we basically rounded up to 2, right? So we're saying that there may have been some experimental error, and so we're going to round up to 2, 1.98 to 2. However, in this case, we're saying that 1.33 is too far from 1, right? And so we cannot round up, we cannot basically say that it's 1, right? In fact, it's quite close to 1 1/3. And so because of that, it is suggested that we multiply the ratios by 3 to obtain whole numbers, right? So 3 times 1, 3 times 1 1/3, and 3 times 1 here, right? And if we do that, we'll get a ratio of 3 to 4 to 3, right? And that is our empirical formula. All right, so what's the point in getting an empirical formula if we cannot convert it to our molecular formula? So how do we do this? Well, we can obtain the molecular formula for any compound from its empirical formula if we know either the molecular weight or the molar mass of the compound, which is basically the same thing, right? And so the subscripts in the molecular formula of a substance are always whole number multiples of the subscripts in the empirical formula. Now, this multiple can be found by dividing the molecular weight by the empirical formula weight, right? So what we want to do here is to find we're given normally the molecular weight, and we know what the empirical formula is, so we can calculate the formula weight of the empirical formula, right? And then divide them, as we see in this equation here, to get the whole number multiple. Let's see if we can make it a little bit clearer on this slide. So, for example, the empirical formula for ascorbic acid was determined to be C3H4O3, right, as we calculated. This means that we can calculate the empirical formula weight, right? And we know, we should know our periodic table at least. We should know carbon, hydrogen, and oxygen, the atomic weight. And, or we can say atomic mass unit, right? It's 12. And so for carbon, and so 3 times 12 plus 4 times 1 for hydrogen, 3 plus 3 times 16 for oxygen, and we end up with the empirical formula weight to be 88 atomic mass units, right? And so the experimentally determined molecular weight is 176 atomic mass units. And so we're given the molecular weight. And so to find this whole number multiple that we speak of, we just divide the numbers by each other, as we see here, which is 176 divided by 88, and we get 2. Consequently, we multiply the subscripts in the empirical formula by this multiple in order to get the molecular formula, right? So 2 times 3 gives us 6. 2 times 4 gives us 8. And 2 times 3 again gives us 6. So we have therefore successfully converted our empirical formula to our molecular formula. All right, so let's see if we understand what's going on. Mesethylene, a hydrocarbon found in crude oil, has an empirical formula of C3H4 and an experimentally determined molecular weight of 121 atomic mass units. What is its molecular formula? So this is how you know if you understand, if you can go ahead and do the calculation before looking at the answer. All right, so we have 3 steps, right? So the step 1 is to calculate the formula weight of the empirical formula. So it's C3H4. And so 3 times 12 plus 4 times 1 gives us 40 atomic mass units. And then step 2 is to calculate the whole number multiple using given molecular weight and result from step 1, right? And so our given molecular weight in the question was 121 atomic mass units. And so we divide that by the answer from step 1, and we get the number or the result to be 3. And then our final step is to multiply the empirical formula by the result from step 2, which is 3, right? And so we're given the empirical formula, which is C3H4, and therefore if we multiply by 3, so 3 3 is 9, 3 4 is 12, we get the molecular formula of mesethylene, right? Which is C9H12. All right, so we have come to the end of this lecture, and that's all for now. Thanks for watching, and see you next time.